Welcome to the third week. This is the third week of this year's Science and Cooking Public Lecture Series, and we're very honored to have Bill Yosses, who is the White House pastry chef, who will talk in a minute. But first, you have to listen to me first. And I was just telling to Bill that usually I get nervous talking to huge crowds of people, except that I know no matter how bad this is, his is going to be great. So I have very little pressure on me here. Okay, so the science topic of the week. So my job, for those of you who haven't come to this in the past, my job in the next 5 minutes or so is to rapidly go through some of the science concepts that we're covering in the class this week to complement Bill's lecture. Some of the science concepts he will also go through himself, but I'm just going to very quickly go through and tell you what we're doing, and then we'll introduce the main show. So the first step, though, is to thank our sponsors. So this public lecture series has been sponsored generously by a number of different entities. So Jose Andres' Think Food Group sponsors us now and from the very beginning. So the Alicia Foundation, which is the research arm of Ferran Adrià's in Barcelona. Zurtoli is an olive oil company in Spain that has contributed to the travel of all of the Spanish chefs. Whole Foods, River Street, you should all go and shop there. They've donated food for the labs, both in the class and for tonight. Taza Chocolate, you will see why we are thanking Taza Chocolate later on tonight. You can imagine. The Boston Honey Company. Do you see this thing of bees? And finally, Oya, which is a restaurant in Boston, has helped us in many ways. Okay, so the theme, so every week we have a theme, we have a scientific theme, we have learning objectives, and we have an equation. So the theme of the week is that of phase transitions, and the idea that we're trying to get across in our class this week is that molecular interactions, that is interactions between the molecules, determine the phase behavior of material. Now, cooking often involves phase changes of food. Some of these phase changes are simple, such as the boiling of water, and others are more complicated, such as some of those that you will see tonight. We then have a bunch of learning objectives that cover this, and then we have this equation. And as you all know, it is tradition that you should clap when you see an equation. Now, the question that you should be asking yourself, though, is does this equation have anything actually to do with the cooking that we're going to be talking about? And we feel that it does, but it's us to but we're not going to have time to convince you in this abbreviated presentation, but I will try. Okay, so what is cooking? So if you look in the Oxford English Dictionary, they tell you that cooking is to prepare food by application of heat. So if you're a scientist and you look at a definition like this, I mean, first of all, it's sort of a very narrow definition. I mean, I don't know about you. Do you always apply heat when you cook? No, see, he cooks without applying heat, so that's a pretty lousy definition. But anyway, we like to recast things as plots. That's what scientists do. We take ideas that are simple and we recast them as incomprehensible plots. Now, this plot is hopefully a very simple one. So there's a critical temperature, and below the critical temperature, the material is uncooked, and above it, it's cooked. And that is a simple example of a phase diagram. There's a critical temperature at which it happens. Now, you know of phase diagrams in your daily life. So here is an example of one that you all know very well. Sorry, there seems to be a bit repetitive nature on the slide. Solid, solid, liquid, liquid. So this is the phases of water. And what you know is that water freezes at 0 degrees, it becomes ice. And at 100 degrees, it boils, it becomes a gas. And this is an example of a phase diagram. Now, if you had some need for gaseous water, steam, in your eating, then you would call that cooked. Now, of course, so you can ask. Now, I know none of you, well, maybe some of you have a use for this in cooking. This actually does have its use. But as scientists, what we like to ask is why? Why does the phase diagram look like this? Why is it that there's a transition at 0 degrees? Why is it a transition at 100 degrees? And the answer to this comes from thinking about the molecules that make up the material. So the structure of a solid is very different than the structure of a liquid, which is very different than a gas. And so we're only talking about water, which is the most important cooking material. That's fair, right?
It's the most
I mean, without
universal.
it, without it, we would be in trouble. I mean,
yes, we would be in
trouble without it.
Yes,
So it's sort of
I
necessary.
agree with you.
But it's not what you. But these sorts of transitions occur when you cook all sorts of foods. That things get more complicated. But it's the same sort of idea. But anyway, I wanted to give you all, just in the spirit of fun, a quiz. Okay, so I'm going to show you, so here's a quiz. I'm going to show you some number of movies, and I'm going to show you, and these movies are simulations, they're computer simulations of water. And the water is either going to be a solid, a liquid, or a gas. And you guys have to tell me which it is. Okay? That's the quiz. If the movies work. I haven't tried this. Okay, let's see. Oh, yeah, this is going to work. Okay, here we go. But no, you have to, is it a solid, a liquid, or a gas? Okay, who votes solid? Who votes gas? Who votes liquid? Okay, so gas had a couple votes, and liquid had most of the votes. So no, it sort of is a little confusing to tell the difference between a liquid and a gas, but it's certainly not a solid. So okay, so that was pretty good. It actually turns out that's a liquid. So the majority won. That's pretty good. The majority is not always right, but they are here. Okay, now this one's really difficult. Okay, here we go. Ready? Okay, so who thinks that's a gas? Who thinks that's a liquid? Who thinks that's a solid? Well, everyone voted for solid. Okay, very good. We're doing pretty well. Okay, and now finally, this is the last one. Okay. No, this is more tricky than this. It's a solid. Look, but look what's about to happen. Somebody's raising the temperature. You see the temperature's going up. Ah. It's going up. Now it's a liquid. Now you're going to see it become a gas. Ah, now it's a gas. You see what happens when it's a gas? And now we're going to cool it back down. Look at that. It's going really fast. That's a gas. We're cooling it back down, and look what's going to happen. It's going to become a solid. See that? It doesn't look exactly the same as it did before. It takes a little while for it to get there. See, it's rearranging. I have a question for you, actually, while this is going. This is relevant for tonight's lecture. Window glass. You know about window glass? Is window glass a solid, a liquid, or a gas? This is relevant, right? I'm being relevant. I'm not totally off topic. Okay, so who votes that window glass is a gas? Who votes that it's a liquid? Who votes that it's a solid? Okay, so there seems to be some disparity of opinions, and we'll talk about that a little later on. I'm going to leave that hanging. I mean, it is true for those of you who voted that it was a liquid. I mean, suppose I gave you a very, very thick pane. Has anyone ever stood on window glass? Well, I mean, has anyone ever gone, there's this building in Chicago where you can like go out over this big glass thing and stand there looking down? Has anyone ever been there? Apple Store has this. Did you tend to stand on liquids? So do you stand on liquids? Let me think about it. That's pretty intense, right? You're actually putting your weight on the thing. I don't know if you go around standing on liquids. Anyway, you should all think about that. Okay, so I have like 3 more minutes. Sorry, am I taking up too much time? No. Is this okay still? This is okay? Okay, so let's summarize what we just saw. So the phase behavior is determined by 2 things. It's determined by the competition between molecular motion, that is the molecules were jiggling around, and they were also sticking to each other. And the deal is that when it's a solid, when sticking wins, it's a gas when motion wins, and liquid is somehow intermediate between these 2 extremes, and there are bonds between molecules that determine this. And essentially the equation of the week, which you all must clap for again, summarizes this idea. It summarizes this very simple idea that phase transitions in materials are determined by the competition between jiggling and sticking. Now, the reason that we like this equation, actually, in truth, the people who teach this course have mixed feelings about this equation, if you want me to be really quite honest. But anyway, the reason that I like the equation is because even if you were going to talk about what Bill is about to show us, which is magic with sugar and honey and all sorts of things, there's a sense in which this equation still holds. It's basically this concept of sticking versus jiggling. This still goes on even when the materials are much more complicated than water and when the sort of simple simulation picture that I just gave doesn't work. Now, in the class, we go into this in more detail. We talk about fats. We talk about cocoa. We talk about all sorts of things. But here, we don't have time for that. I was going to tell you about the pressure dependence of phases, but I'm not going to do that. I was going to tell you about phase diagrams. You know, the boiling point depends on pressure. You all know that if you go to the top of a mountain, it's different than at the bottom of the sea. And, you know, chefs use phase diagrams to their advantage. I don't know, does anyone pressure cook? So this shows you why pressure cooking is such a great thing. If you increase the pressure, look what happens. The boiling temperature of water goes above 100 degrees, which means that you're heating it at a higher temperature. So, you know, one of the problems with the boiling point of water is you can't heat things in water more than the boiling point because it's just boiling. So that's a bummer. But if you pressure cooker, it goes up even higher. Last week, and actually even this week, look at this. Look. See? Look. So there's a rotovap. That's fact. So this thing is going to decrease the pressure. And when it decreases the pressure, the boiling point is going to go down. And Bill is going to explain to us why he wants the boiling point to go down, right? So I mean, this is just magic with the phase diagram of water. And so let's see. So there's that. And so okay. So finally, that's it. I'm done. Except that I want to introduce Bill. So Bill is amazing. He's been coming here. This is the third year in a row that Bill has come and lectured in this lecture series, and we're very grateful to have him. And we're very honored that he continues to come. But one thing I want to tell you about Bill, and I think he's going to talk about this a little too, but I just want to show you a couple of slides and pictures of this, is that this summer, Bill was one of the people that was instrumental in starting a program here that was science and cooking for kids. So Gabe is there, and he did, and Naveen, and Jason is someplace, and Christina is someplace, and Tracy had, and there are all these people around. They sort of made this really amazing thing where there were kids that were young kids came and learned about science in terms of cooking. And I just have a couple of pictures to show you. So these are the kids. There's Bill. There's Jason. There's Gabe. Jason Bond, you here? Rolando from Clover. But what's really great about Bill, and I was going to actually show the clip from this movie. There's this movie that Harvard made about this. When Bill starts, he says, "We're going to have fun," and I didn't have that. But this is Bill having fun and having fun with the kids. And you're about to experience this right now. And we're really grateful that you came, and we're grateful that you've put just so much energy into this endeavor. And Bill.
Thanks. Thank you very much, Michael. Thank you to Harvard for this amazing program. It just seems to get more and more rich and layered as the years go on, and it's just been a wonderful thing for chefs. It's been a wonderful thing for students and for the general public who enjoy these lectures a lot. I'm honored to be here, and yeah, the class this summer was incredible. I'm glad that you did not save the video of the Zumba class. I don't Zumba very well, but those are very flattering photographs, so thanks for showing those. I'm going to continue a little bit in the vein that Michael started in. We're going to talk a little bit about the science as best we can, because one of the things I always like to start out with in these classes is it's very important that we as chefs, that we learn something from these classes, and one of the ways we learn it is how it affects our food, of course, and how we can cook with it. So in order to understand that, it's helpful for us to understand the size of things that we're talking about. Basically, we sort of in our minds, we say, it's all very small, you know, what Michael was talking about and how those molecules line up. But there is really a vast difference between small and super small and super, super small. So Naveen was helpful in drawing up these diagrams here, which indicate not only the size of what we're talking about, but also what those phase transitions look like as they develop. So let me be more clear. So one of the smallest elements that we work with is water. So H2O, two hydrogen atoms and an oxygen, and linked like this. So that's the smallest sort of category. I mean, unless we go into, I don't know, electrons or Higgs boson or something like that. This is where we start out with. So, and as Michael explained, there's ice, liquid water, and steam or vapor. So one of the questions that I think is interesting to think about is if we take a chunk of ice, say we took a chunk of ice that fit into this pot here, and we put the ice in there, and we turn this on, we let it melt down into water, and then turn into steam, boil it away until it turns into steam. It's interesting to think about what takes more energy? And we'll do the hand raise thing again. Does it take more energy to melt a block of ice into liquid water or to turn that water into steam? Who thinks that it takes more energy to melt the block of ice? A few of you. And who thinks it takes more energy to turn that liquid water into steam? Right. And one way to think about that is because the amount of time that it would take. It would take a bit of time to melt the block of ice down into liquid, but it would take a much longer time for that thing, even at a boiling temperature, for all that water to evaporate. Even so we'd have the same temperature, all that water to evaporate. It'd take a lot more energy. And in your classes, if you're students, you'll be able to look at a graph where that's how it's delineated. So size-wise, we're talking about the smallest when we talk about water. And then one of the things that interests chefs is fat. Who's not interested in fat? One way or another. So, and one of the things we'll talk about later when we get to the sort of demo portion or experiment portion of the class is cocoa fats, which is cocoa butter, and how they crystallize or how they form crystals from a nucleus. And that's a pretty small formation, but it's much larger, in fact, 10 times larger than a water molecule. It's a very important thing for making chocolate or for tempering chocolate. And we'll get into that too. I want to explain more about chocolate and what tempering means and what are what's the composite of chocolate that makes it hard here and yet liquid when if I put this in a microwave. So something that can be a block like this, or can be a liquid if this is heated, similar to water, but not the same because the crystallization happens on a larger level. Another thing we're going to talk about that is especially important for I don't know what we want to call it, modernist cuisine or just it's the way people cook today. Most chefs are using one or two of these techniques. So we can call it molecular gastronomy, whatever you like. But gels and spherification, okay? It's a very unique way of preparing something. It doesn't take heat, as we said before, so already the encyclopedia is wrong about what cooking is. I would still call it cooking. I would still call it cuisine. But we're able to take, again, these molecules, these liquids, and with the addition of a certain gel, we're able to transform them into something very interesting, and we will show you how we do that. Here's an example of alginate. So this is a algae. It's made from seaweed mixed with water, and then this is a salt, gluconate. And what we do is we made a honey infusion, we'll call it. It's honey that we will get to in a minute when we talk to Nick. And with that honey infusion, we add a salt to that gluconate. In themselves, they don't react with liquid. So this is still liquid. This is still liquid. And but when they come together, when this goes into this, it immediately forms these gels. So these are called polymers. These polymers form, and in fact, they will form so quickly that when I take a spoon of this, which has the salt in it, and put it into the alginate, the sphere forms immediately because that gel activates and forms a very, like a membrane, just like for an egg yolk. It forms a membrane, but remains liquid in the center. So we will see that happen right before your eyes. Okay, so that's another way of chefs using these procedures to manipulate food. And we wanted to point out that these are phase transitions, which is our subject today. Phase transitions as opposed to chemical reactions. Chemical reactions, if you were in grade school when you mixed the vinegar and baking soda, that's a chemical reaction that changes. But these changes are not chemical reactions, they're phase transitions. So now we're up to an even larger process, which is still not visible to the naked eye, but now we get up to one of the other sort of techniques of modern cuisine, which is foams. That could be a chocolate mousse. It could be, sometimes we add lecithin to a fruit powder, and then we use either immersion blender or a mixer to it, and we make foams. Why does a chef care about foams? Well, just like a sommelier with wine, you swirl the wine in your glass to introduce oxygen into this substance, and it accentuates the flavor. It brings the flavor out when it mixes with oxygen. Well, likewise, so does that method when you're making a foam, a chocolate mousse. One of the reasons it tastes good, not only because of the texture, which is smooth, but because it's aerated, and you're mixing that flavor of chocolate with oxygen, and it releases more of those flavor molecules. So that's why a chef wants to do that. And we're on a much larger scale now, times 1,000. I mean, we started out here with an atom, and now we're into the realm where you can actually see some of these bubbles almost with the naked eye, or just with a normal microscope. One year we did put a layer of this chocolate mousse in the microscope, and on our screen up here, I mean, they were basketball size, and that's just with an ordinary magnification of 100. So interesting to think about scale. I mean, we're talking down here, you're talking about the nanometer. You measure in a nanometer, which is 1/1000th of a meter. 1/1000th of a meter. Okay, and when we come around to here, we're talking about micronometer, so 1/1,000,000th of a meter, and then here it's visible to the naked eye. So foams and mousses are here. On a completely different scale, here we're talking about the formation of those molecules. Okay, so when we're talking about ice, for example, we have it in this blocked sort of form where it's solid, it doesn't move. You drop it on the floor, it may crack, but it doesn't flow. When it's turned into a liquid, the water runs on the floor, or as we saw in Michael's slides, how it can turn into a gas. We're going to see how those forms also react with food. So this would be a sugar crystal. So, and there too, if you look at it in a microscope, you see a very angular kind of formation. Sugar is very, very structured like this, and when it's cut, it cuts in very angular ways, geometric ways. When we get to this level, this is sort of the a liquid level or glassine, and that's where we are with this sugar. This sugar has been cooked at not a very high temperature. It was cooked at 160 degrees centigrade. So it sort of behaves like a liquid, something between a liquid and a solid. And what chefs do with this is they make sugar decorations, and I'll show you how to do one in a moment when we get to the experimental phase. So, and you also have another effect that as you twist this sugar and pull it, it develops a shine, and that's what we're looking for because we're making decorations out of this. So we do these, for example, the most classic one, and it's been around for a long time, is we make a green apple by using an air pump. And so we take some of that, which I'll show you how to do. We make a green apple with that very liquid sugar, and then it becomes a crystalline structure like this and stays firm. So the purpose of this is then we make a little hole in the bottom. We fill that with, I don't know, vanilla ice cream, apple sorbet, or maybe a mousse or something like that. And we can get this very, very thin because you can see how pliable that is if we get it very, very thin. And then so you can just barely touch it with a spoon and it collapses. So we'll get to that when we get to the more experimental part. So that I just wanted to do that as a follow-up to Michael's presentation, and we're going to show each of those processes in more detail. But first, although I've been talking for about 15 minutes, I want to introduce myself. So I'm Bill Yosses, and I'm the pastry chef at the White House. I'm honored to be part of Mrs. Obama's team, and one of her most important initiatives has to do with childhood health. And if you can imagine this amazing person, so in 2009, she moved into the White House. Just kind of put yourself in her shoes. Okay, she has 2 young kids to put in school, all the furniture to move, moved into this really old house that, you know, a lot of things don't work really. They fix it all the time, but it's old. And your husband got this just really huge job. Given all that, she called all the chefs into a meeting and she said, I would like you to help me make food and healthy living for young people the most important thing that we talk about. And so with all this going on, she had time to do that. Not only that, but then she started, with the help of Sam Cass, who is the domestic policy advisor, she planted a garden in the South Lawn. And the garden has become, it's not only a very real garden that we use to cook with, but it's also a great symbol of community and of how we can get kids to eat better, and face it, grown-ups too. So we have, for example, a program where we bring school kids into the garden. We let them see that, oh yeah, tomatoes grow on this vine, not under cellophane. And so it's been an incredible experience. I'm honored to be part of it. And one of my favorite images from that is what you see up there. So there was this guy who brought these balloons. Part of her initiative, which is called Let's Move, is about exercise and getting kids moving. And as we often tell them, there's this new thing. It's called outdoors, and you don't have to plug it in, and it's always there, and it's free. And so, get out there and enjoy it. So this was one of her guests, and it's in an amazing room. One of the things we love about the way Mrs. Obama invites guests in is that this room is called the Diplomatic Reception Room in the White House, 200-year-old room. The room was actually renovated by Mrs. Jackie Kennedy. What you see on the walls there is a lithograph painted in 1830 by a French artist of different parts of this new world, the new country of America. So over here, you see it's actually West Point, if you can see the soldiers up there. And over on this side is what's called the Natural Bridge in Virginia. It was a bridge that was actually owned by Thomas Jefferson. He owned the real estate at the time. It's a geological formation. And anyway, we'll get back to Thomas Jefferson in a minute. But so this was her program, Let's Move, and there's a very good example of it. Another good example, look, let's face it, she will do anything to get people involved. So she had Jimmy Fallon come, and they had this sack race across. Now, that's the state dining room, okay? Presidents, I don't know, everything, emperors, kings, queens have been received in that room. The painting on the wall is a Gilbert Stuart portrait of George Washington. It is the painting, the only thing that survived the burning of the White House by the British in 1814. During the War of 1812, it was saved by Dolly Madison, who had it pulled off the wall and taken away. But as much as all of us as Americans can feel proud and respect for those things that happened in that room, Mrs. Obama is committed to using everything that she can, all the images, to get kids active and to get them on a healthier path. This was this summer at the Olympics. Mrs. Obama hosted a party at the ambassador's residence in London, and she had a tug of war between two groups. That is, I'm assuming she won. And now to the garden. Okay, and also back to Thomas Jefferson, because we have an incredible history in America, really, of being an agricultural country. And not only Jefferson, but Washington, of course, was a farmer. Even Adams had a small garden, and all of them were very interested in horticulture and agriculture. Jefferson and Adams made a trip to England, in which they sort of visited all the gardens to compare and to learn about how to grow things. And they used not only horticulture and the foods that were grown, but they used cooking. Cooking is really a part of our American tradition, and nowhere is it more evident than in the writings of Thomas Jefferson. So this is an example of an artichoke plant that we have in the garden this past summer. It's a French artichoke. Jefferson was known for bringing plants from Europe, from all over the world, Caribbean also, and planting them in Virginia, and writing to his friends and sharing the seeds. And this was most of his life after he was president, was devoted to his garden. So imagine this. Okay, he wrote the Declaration of Independence, went to the Constitutional Convention, straightened that out, president for 8 years, sent Lewis and Clark to the West, discovered the entire West, and basically sort of just defined America. So, but as he grew older, Listen to what he wrote to a friend of his, Charles Peale, who was an artist at the time, who was also interested in many of the subjects that he was, truly a Renaissance man. So this is the letter he wrote to him. I have often thought that if heaven had given me a choice of my position and calling, it should have been on a rich spot of earth. No occupation is so delightful to me as the culture of the earth, and no culture comparable to that of the garden. Such a variety of subjects, someone always coming to perfection, the failure of one thing repaired by the success of another. And instead of one harvest, a continued one throughout the year. I am still devoted to the garden, but though an old man, I am but a young gardener. So not only could he think, he could write. Amazing person. He's been an inspiration for us. We have many of his heirloom seeds. I'll see, there's a picture of Mrs. Obama's garden on the south grounds. What you see there in the plastic are what's called hoops. We grow the garden 12 months a year, even in the wintertime. And Washington, D.C. can have a pretty harsh winter. We can grow many things under those hoops. It's a really beautiful garden, and one that has given us chefs. As you can see, 2 chefs there. They're harvesting vegetables for one of the state dinners that we had. Here's Mrs. Obama, a very interesting part of the garden. This was actually, the people who are with her are Native Americans, and they brought their kids, and what they're planting there is called the Three Sisters. It's a Native American system of growing, which is a symbiotic relationship between 3 plants: corn, squash, and beans. So the corn is planted, and on that stalk of corn, that corn stalk becomes the stalk that the beans crawl up. So beans are planted next to it, and the bean can crawl up that stalk. Squash is then planted on the same plot, and the squash then has very big leaves and forms a ground cover, which protects the grounds from weeds growing. And also the beans return nitrogen to the soil, which the other 2 plants need. So it's a great message for kids about cooperation, about symbiotic relationships, and also about this heritage of the American Indian and the systems that are so successful. In fact, that plot was a little too successful because the squash just was so prolific that it covered like 3/4 of that garden that you just saw. And but we were so encouraged by it, we just kind of let it go the way it was. Here's these 2 strange-looking men are standing in front of Monticello, which is Thomas Jefferson's home in Virginia. The man next to me is Peter Hatch. He was the gardener. He has been the gardener at Monticello for the last 35 years, and he is really the embodiment of Thomas Jefferson himself. He talks like this. He knows everything about the garden, and it's a 1,000-foot garden that he has helped to transfer some of those heirloom seeds to the White House garden. So one of the things that you will see that we talk about is something that Jefferson wrote about, and they're called fish peppers. I have some in here. They're just a very hot pepper, but I really kind of love this combination of this Jeffersonian belief in agriculture and food mixed with a modern sensibility. What we're able to do with these peppers, which are very hot, is, and I like hot peppers, but one of the things we're able to do with this process, this is called a rotovap, is to distill the flavors out of a pepper. So this is something that, distillation is very old. It can, they do it in Kentucky all the time, whether government knows about it or not. This distillation is of hot peppers, and we're able to take out the flavors of the peppers without taking out the capsaicin, which is the hot part of the pepper. And so we do that with this, and we'll refer back to Michael's presentation, because the reason we use this machine is that we can boil these peppers at a very low temperature, room temperature. This can come to a boil. How do we do that? By lowering the pressure in this beaker. So by lowering the pressure, we can boil something at 70 degrees Fahrenheit. Why do we want to do that? Well, cooking transforms and often destroys a lot of flavors that we would like to keep to put on the plate. peppers are one. Another example would be a lemon verbena. Now, lemon verbena is a great herb. It's very wonderful aroma, lemony. But as soon as you cook it, it disappears and turns brown. Even as soon as you clip it off the garden, if any of you grow it in your garden, it wilts right away. It's just a very sensitive and delicate plant. But what we're able to do in here is we're able to distill it without raising the temperature. We can remove the flavonoids and all those active ingredients. And so we've created this clear liquid here, which is the very essence of lemon verbena. Remember, just to back up a little bit, okay, when you're cooking in your kitchen, oh, that smells great, you know, the roast chicken, the herbs, and cooking away. Well, all what you're smelling is molecules that you're removing from your dish. So what if we're able to keep it in there and put it back in? So that's the kind of thing which is really exciting for chefs. And that's what this machine does. So, and afterwards, if you want to come down and you can open this up, it really smells like natural lemon verbena. So it's something that I, for example, as a pastry chef, could put into a meringue. If I was making a meringue with egg whites, they would pump all the air into it, but it's very delicate, even though we put sugar in it and it's stable. If I were to put just a few drops of oil or a few drops of water in there, I would lose all that volume. I would go from a meringue that was that high to about that high. But this is so concentrated, I really just need a drop, and I can really bring that flavor out into a meringue. And there's many, many other uses along with that. So that's what we do with this machine. We lower the pressure, and we're able to boil at a low temperature, and then the most volatile of those flavors are captured in here. What this machine does is, okay, it boils at a low temperature. The steam then goes through here, and this is a coil which refrigerates it or freezes it, so it condenses back into a liquid and drops into this beaker. Amazing machine. We got as far as Monticello. Okay. Now we're up to Nick. This is an amazing part of our garden. I'll be brief. I'll just say that we had a carpenter who worked at the White House, loved bees, raised bees, and offered to bring a beehive next to the garden to increase the pollination, because that's one of the byproducts of having a beehive there. And I found it so exciting, and I've been working with that guy ever since. What you're looking at there is a very interesting picture of a way of growing queen bees, because one of the ways that we try to fight the colony collapse disorder is by improving the genetics of the queen bee, and naturally they can fight the pests and things which kill bees. So one of the ways to do that is through genetics, not through fungicides, insecticides, and all the things that people use to artificially help bees during the short term, but is killing them in the long term. This is a queen bee, and you can meet one up close and personal after the session. I'll leave it to Nick to explain more about bees and beehives. It's all yours. Thank you.
Thank you very much. Hi, my name is Nick Delaney. I represent the Boston Honey Company tonight. I'm an apiarist for them. I started as an apprentice about 4.5 years ago. We're based out of Holliston, Mass., but the 1,200 colonies we run are in Stowe, Concord, Lincoln, Sudbury, all over eastern Massachusetts. We have probably upwards of 3 dozen yards. These bees cover places from Battle Road to the Charles River, or just to downtown. When I used to live in Brighton, I even kept a colony on my apartment and got really good cut comb, because cities only plant ornamental flowers, and those things just make great honey. So I brought the gals tonight. I really recommend everybody come on down, take a look. We put a yellow dot on the queen tonight to help you locate her fast. Take a look. She's really, as Bill's putting it, is a fascinating and tremendous little animal. They all are. They are screened in. They are locked shut. There's a screw to bolt that in. We have C-clamps. In case you're nervous, I also have tape, but only so much. So be careful about that. We started as a company. We're a small family-owned business. I'm the only non-family member, but you know the joy is, as long as everybody's happy with your work, you get to feel like a family member. So my boss, Andy Riseska, who started Riseska Apiaries, used to be a house painter. And this is to show what Bill's talking about with when you get in touch with the environment and with nature and community. Andy saw in Newton a couple of colonies at a rabbi's house and began to talk to the rabbi about it. Come 1995, he had his first colony and started going from there. And bit by bit, the garage disappeared, the painting business disappeared, and he moved out. Set up operations, and we continue to grow and really strive to produce honey. That's what our crop is. We do pollination for orchards and farms, and our bread and butter, though, is honey. And these days, we try to experiment from just doing a raw wildflower to doing raw varietals. We've started bringing some of our bees down south to a property in Georgia we acquired to give them a light winter to help, as Bill's saying, expand the colonies, expand the genetics, be able to build from there and bring them back right away in the spring to make honey up here. And then we get a little bit of things like gallberry honey, which is from the south, or Tupelo, things like that. Now, with bees, what is so enjoyable is exactly, again, what we've all been talking about, whether you're talking about the science of what's going on in there, or you're talking about the community and the event of it. Because of things like colony collapse disorder, people have gotten so interested in beekeeping these days, but thankfully that's not just a morbid curiosity. It's really grown. It's the same with any kind of movement towards local and agricultural. People are genuinely interested. It's good for all of us. It helps you find better foods. It helps you find better ethical processes for bringing those foods to bear. And it brings you in touch with each other, and it brings you in touch with your farms, and it keeps us all supported. Something like Michelle Obama and the garden and this colony and any other colonies from it, it reinforces that we're all dedicated. It reinforces that we all enjoy it. It's an easy sell. That's a fascinating thing. And it's fascinating that even if you can't see it and it's, 2 miles away in somebody's bushes, it's going to still be just as lovely. Now, a quick to go past that and into what exactly bees are doing inside there. First of all, yeah, there is one queen in a colony. The majority of a workforce, they're all female workers. The only difference between the queen and those workers is they don't have the same amount of royal jelly in their initial diet, which keeps those workers from developing ovaries and being able to become mated and produce more bees. Then you have your drones, a small percentage of the population, those are the males. They exist to mate, and after that, their life ends. And if they don't get that far, come winter, the wings get chewed off, they get shoved out of the colony because they're just going to take resources up. So it's a community effort, but some things hit the road at some point. Inside that queen, as Bill was mentioning, when she's mated, she'll lay the entirety of those eggs. She can lay 1,500, 2,000 eggs a day if she's a strong queen, and the genetics are important. You can buy a honeybee queen for 15 bucks, or when you're starting to raise queens, you can buy one for $500, just a single queen. Genetics are important. It's continuing that rather than working at using harsh pesticides or using any kind of abusive practice to instead work with the systems that have been working for so long in continuing and propagating a species and let them continue. Help those genetics along and see how those bees react in a much stronger and better way to anything such as mites or colony collapse disorder. She'll lay the eggs, she releases a pheromone that helps keep all the bees in kind of almost thrall and in calm. And when that starts to get too large, it's time for her to take off. So she'll take about half of that workforce and the new queens that are being raised. One of them's going to emerge, either try and kill all her sisters somewhere before they hatch, or just fight it out and then take dominance. They'll start a new colony. That new queen becomes now the new progenitor of that colony, and everything continues from there. And the worker bees have the tremendous responsibility from day one of hatching to go from cleaning and preparing cells for new bees, new eggs to be laid, to creating the hygienic nature of the hive, hauling out anything dead, keeping things clean, sealing stuff with wax and propolis, taking off pollen from incoming foragers, helping to evaporate the moisture out of incoming nectar to turn it into honey on top of the enzymes bees add to it, and then that becomes their food system. They create honey as their carbohydrate. They take pollen, mix it with a little bit of honey to make pollen bread, that's their protein, and then they forage for water. And they do that in numbers that range in probably an average hive around 60,000 individuals. And they can grow from there. And they work in this nonstop, madcap way because winter's coming. They need to have a ton of stores to keep a lot of individuals going until that point. And then we come along, we rip the roof off, we steal a couple floors, all the good things on those floors, and run away. So it's a fun agricultural process, but it's pretty wild in the sense of wild. So the beauty is with honey, and what makes it so fascinating these days, and I think why with everybody's attention, it's left from the condiment spot on the table to becoming something people want to cook with, they want to play with, they want to taste. It's just like wines, it's just like cheeses. The nectar matters. When these bees go out to become pollinators, they're attracted to these colors, they're attracted to these scents. They move out, and these foragers are responding to the scouts. Scouts go out, they spot these things, they fly in. The front of the colony is a dance floor, is what it's called. That scout begins to dance. She's wiggling, she's waggling, she's showing off how good the flowers she found are. Then she starts pointing her abdomen, and that's giving delineation off of the sun. And those bees are now learning where to head out. They take off en masse, they proceed to get as much as they can while it's there, while it's flowing, and put it all in. Something strong enough is how we get things like orange blossom honey, clethra, black locust, Japanese knotweed, buckwheat. They'll make an abundance. Best part of the job, we get to taste the honeys that there's not enough to make to the table. A little bit of maple honey, a little bit of dandelion honey. It's fantastic, very fantastic. You get stung in the lips sometimes, but. So they make this rich and complex food for themselves. And you can think about that in sort of community and cooking. They're crafting it. They go out, they get nectar, it enters their honey stomach, they begin to add enzymes, and then those enzymes, as they come back, they proceed to start putting the nectar that they've gotten back into these cells. These cells, they'll then drink it back up, regurgitate it again if they need to get the right mixture of enzymes, and then they'll proceed to beat their wings and help force evaporation to lower the moisture content. They're changing the pH, things like that, and they're crafting a really fantastic food. All we do is we gather it, we extract it, and they did all the work, really. It's what transformed what I thought would be a lark, a little 6 months here and a weird job off of Craigslist, into what I thought now is probably going to end up being a prolonged, difficult, but absolutely enriching and absolutely lovely job. So thank you very much for having us tonight. Come down, please, later and ask questions.
Thank you, Mike. Thank you. Great. We're so happy to have had Nick. Thank you very much. You know, anybody that is willing to travel miles and with that in their back seat needs. What's that?
It gets a buckle.
It gets a buckle. Deserves some credit. The reason that we recommend artisanal honey or local honey is that, remember, these bees are going out and collecting pollen from this area, the local area, wherever it is, and so you are ingesting minute amounts of pollen from the area in which you live, and that is kind of a vaccination against allergies, because most people with hay fever and things like that, what you are reacting to whatever the a weed is that is in the atmosphere. So by eating local honey, you are ingesting a little bit of that, a little bit of those allergens, and you're developing a resistance to it. So we this course has led to so many, as I mentioned earlier, so many different and very enriching experiences. One of the people who was with us in the beginning, Amy Roat, has since moved to UCLA, where she has started a program there called Science and Food. And so last year we had just a great group of people. One of them was Renee Redzepi, who is the owner of the restaurant Noma, which has been recently listed as the #1 restaurant in the world by San Pellegrino. He follows a sort of an interesting philosophy of foraging, and he has people that go out into nearby areas, and they not only buy shellfish and fish and fruits and vegetables and things like that, but he also is experimenting with insects. So Renee sent a box of crickets from his restaurant to Los Angeles, and so they were being stored in the science building at UCLA, And apparently a few got out, because now when you walk through the science building, you hear at night you hear the crickets chirping. But I did not taste the cricket dish, but I'm told it was interesting. So, no, I'm sure it's great. I've heard a lot of great things. So now comes to the part, I think we're okay, yeah, where we talk about how chefs use these things. So, so here, if you have a pen, you might want to take some notes, because we're going to give you some recipes and show you how to use this. So just to start out, we talk about crystallization. Here's an example. This honey, which was used to make this globe water or spheres, has crystallized. It's a little bit different process than sugar crystallization. What happens in sugar crystallization is that the supersaturated water, if you try to put too much sugar into water, it will eventually crystallize. So honey does a similar thing, but as the way Nick explained it too, is that honey is what's called an invert sugar, so it's not the same as just refined sucrose. That's one of the reasons why it's better for you, because it has less fructose, which has been linked to the problems of obesity and other liver problems. But anyway, this is a very nice picture of what crystallization means in terms of honey. By the way, if that happens to your honey at home, there's nothing wrong with it. You just put it in a little warm water, run some warm water over it for 20 minutes, a half hour, and it will come back to its liquid state. So those crystals will dissolve. Not a problem. So crystallization also refers to what happens to chocolate when we temper it. And I wanted to talk a little bit about what chocolate tempering means and why we have to do it. Oh, there's another queen. Yeah, I want to talk about. I put all my queen pictures together. So that's at that event where there was a tug of war the night before. Also, just to introduce myself, one of the things we do is, at the highest level, is a state dinner. This was the state dinner for Prime Minister Cameron. And it was a really beautiful, lovely event. You can see Mrs. Obama there, and to her right, George Clooney, just so I can drop a name or two. This is a beautiful photograph, I find, from the south portico of the White House. Prior to the dinner, they invite the Prime Minister for a short party upstairs. And now on to crystallization. Okay, so there's the green apple, a picture of it that was used at actually the Chinese state dinner. And we filled that with ice cream. Just talking about the kind of things we do. Here's a dessert we made for another dinner, not a state dinner, just a banquet, where we use that sugar, the crystallization that we're able to do with sugar, starting with this. This was for an Olympic team. And so that was meant to be the Olympic flame there coming out of that chocolate tart. More crystallization here. This is when we temper chocolate correctly. It means we melt it and we bring it through temperature changes. In case you're interested, we take it from its solid block state. We melt it to about 115 degrees Fahrenheit. Then we bring it down to approximately 80 degrees Fahrenheit, depending on the chocolate. And then we re-raise it back up to approximately 83 degrees Fahrenheit. By going through those changes, we realign the crystals over here. We realign it from a liquid state to a correctly tempered state where it's hard, and if it's thin, it's very brittle. So another way of talking about how chocolate crystallizes is just by taking it from a warm temperature to a cold temperature, and if we stir it at the same time, we're able to blend it with other ingredients. So for chefs, what that meant for so long was making chocolate mousse, and it was a pretty easy recipe. We would take whipped cream, egg yolks. So the lecithin in the egg yolks helps the emulsion. The emulsion to happen. Emulsion is a dispersion of one liquid in another, most often of a fat in water or fat in a non-fat liquid. And the lecithin helps that emulsion to take place, for that dispersion to be more equal. And the more equal the dispersion is, the more smooth the texture is. So I do this recipe each time I do this course, because For me, it has a lot of meaning. It was the first recipe where I really learned some molecular gastronomy and used it to my advantage as a pastry chef. So this was in Hervé Tisse's book. Hervé Tisse is a French chemist who started writing about molecular gastronomy with Nicolas Curti. They are one of the first people to write about this subject, and they were writing about it. There are articles from 1969. So what we're talking about, like 40 years of molecular gastronomy. You know, we often think of it as brand new, but it's been around for a while. Hervé Tisse, in his book, writes about, well, why do you have to use egg yolks and cream? What they're doing is they are a protein which enables the emulsion to take place more easily. You can replace that protein with a little bit of gelatin. Gelatin is also, at least gelatin made from most gelatin is made from animal collagen. So what you can do is replace those others with a little bit of gelatin, which is what we do here. This has to, this gets bloomed first. So the recipe, and if you want to write it down, I'll give it to you, is 200 grams of water, 150 grams of chocolate. When we say chocolate, we mean couverture, like this. And it's preferable to use something with 60% or higher cocoa mass. I'll talk about what that means in a minute. So you take 200 water, 150 chocolate, and 2 grams or about a quarter teaspoon of gelatin. Okay, so we're going to add the hot water, boil the water, pour it over the gelatin, mix the gelatin, and then I want to be sure this is really hot because otherwise it's kind of cool in here. The chocolate is not going to melt. Pour it over the chocolate, and then either with a hand whisk or with a immersion blender, you mix it over ice. So just so you see the whole process coming together, I want to show it to you. This makes a fantastic smooth ganache or mousse that you can see right here. Here's an example of how smooth the surface of it is. So you can make a really terrific ganache. And you have the real flavor of chocolate. You don't have nothing wrong with eggs and cream, love it. But you have here just the flavor of chocolate, and you really have a much more healthful dessert. So we're talking about just dark chocolate here, which has a lot of beneficial ingredients in it. So there's the only fat in here now is the cocoa butter, which is a polyunsaturated fat. All right, you. Induction burners, they're very useful, but they really have a mind of their own. It works by magnetic. You have to have an iron-based metal to go on top of it. So it's the magnetic field that's created that creates the heat, just like those molecules that Michael showed up on the screen there, where they were bumping around into each other. Okay, so here's the mixture of chocolate and water. Mix it together, and then put it in the ice. So what happens now is we're going to introduce air. I'll try not to splash the front row. So you can see it bubbling up already. Actually, maybe I can take it over there if that... Is that camera working? You have to be a little bit of a magician. Okay. Yeah, hopefully that's working over there. Thank you. Good opportunity to introduce two people who were very helpful. Jason Du and Tracy Chang, thank you for helping do so much work over the last couple days. So please give them a hand. There you go. Really awesome partners, and no chef achieves any kind of anything without great people around him. Jason is also a chef himself, and he's going to be opening a restaurant soon, so let me plug his restaurant, which is unnamed at the moment, I think. But keep Jason DOO in mind because it's going to be a great restaurant. And I'm going there on day 1. Okay, so this gives you an idea of how many bubbles are being formed in there. And as they're formed, since it's in ice, let me see if I can let it go a little bit too deep. Yeah, I'll hold it up like this. This gets the idea across. It takes about 15 minutes, so I'm not going to bore you. But what's happening is all of that, all those bubbles are in the deeper part of that liquid are being encapsulated by the chocolate because the chocolate is crystallizing as it gets cold. So they're encapsulated in there, and they form a soft mousse as you see here. So a very interesting recipe. It's one of the first kind of molecular gastronomy recipes that I came across, but it combines so many things. It combines understanding of food, of why things happen, with the ability to redirect them in another way as a chef, and also to come out with something that's very flavorful, different from the traditional, and also more healthy. So I really love showing that recipe. I hope you enjoy it. Again, 200 grams of water, 150 of chocolate, and 2 grams of gelatin. Next, I want to show another kind of crystallization. So we're back into this area here, and what this tells me as a chef is why I need to, for example, keep this mixture very clean. So speaking of which, I'm going to change these gloves. Because you don't want to introduce any speck of dirt into it. Doing so would make it crystallize faster, and it would be an impure crystallization. So what this is sugar that is cooked to 160 degrees centigrade with water, but at that temperature, most of the water has evaporated out. This also has some glucose added to it, which is glucose is the 2 parts of sugar. Sugar is a disaccharide, glucose and fructose. The glucose is an element to the sugar that is more elastic, and it also does not absorb humidity. That is particularly crucial in this kind of decoration because as it sits out in the air, there's humidity in the air, especially in Washington, D.C. So you don't want it to be, it absorbs humidity and it will just actually melt and collapse on you. You don't want that to happen while the leader of the free world is standing next to it. So, I think, well, here's an example of us. That's Chris Comerford in the middle there. She's the executive chef of the White House. Wonderful chef, wonderful kitchen manager. Next to Rachel Walker, one of the assistant chefs there, and some of the butlers serving one of the dinners. Here again, crystallization is what's at work. So we had this, we had a party for the American Jazz Society. So we had Al Hirt drawn in chocolate there. And the reason we're able to do that is because we can take the chocolate through that phase and it holds together in order to serve it behind a piece of cake. This is another crystallization allows us to make Easter decorations. So we always, every year there's, you may have heard of the Easter egg roll. It's 100-year-old, no, more than that. It started in Rutherford Hayes, so that's like 1880. Very old tradition where kids come to the south lawn of the White House and they take a stick and they push an egg down a hill. That was sports in those days. No Xbox, but they love it, and they still do. You show the kids a hill, and they can roll down, and they're happy. So yeah, that's from the Easter egg roll. And here's another beautiful picture of the Germany state dinner. Angela Merkel is at that table. I think you can see Mrs. Obama standing in the middle, the bottom middle. And look at these two. This is the relative importance of the chefs over here. These two minuscule people on the left are myself and Chris Comerford. Okay, more crystallization. This is the, we call it the white chocolate gingerbread White House. What a mouthful. And that's because inside is gingerbread, outside is white chocolate. Because of this ability for chocolate to crystallize, we're able to make very, very precise molds and to shape or carve chocolate so that it keeps the shape of the little rosettes that are at the top of the south portico, along with the windows, and even the inside, even that furniture inside that room is made out of chocolate. That's the imitation of the state dining room. Everything except the little chandelier there, we haven't figured out how to do that. Electricity through chocolate, I think Dave and Michael are working on that now. This is a plated dessert. Again, there we have one of the things we were talking about, a foam, and the top of the plate there, and some beautiful vegetable, or rather fruits that were part of it. Another picture of the Christmas White House, and just one of my favorite pictures from the Oval Office. We call this "Can I Touch Your Hair?" And the president said, well, you're in the Oval Office. Do you have one question that you'd like to ask the president? And his question was, can I touch your hair? He's a mensch. More serious moment, walking into the Oval Office. Oh, chocolate. Okay. Why does chocolate need to be brought back into that tempering system? Why do we raise those temperature and bring it back? Okay, there's a cocoa bean. If you've never seen it, chocolate is a fruit. So now you can all feel better about eating chocolate. You're eating healthy fruits. And it's a beautiful one at that. It's very, very old, been on the planet for a very long time. Oops, that's another fruit there, I guess. Here's Bo. So inside that fruit is are the seeds. They have to be fermented and then crushed. When they're crushed, two products come out of it. So there is what we call in Spanish cacao or cocoa mass. It can also be called chocolate liqueur, but it has nothing, there's no alcohol in it. It's just cocoa mass and cocoa butter. So butter, obviously, although as I said, it's a polyunsaturated fat, it is still a fat. The cocoa mass is the liquid, so it has to be re-emulsified. This fat has to be distributed evenly into the liquid, and to do that, that's why it goes through this temperature change. When it does, the crystals form in a way that make it shiny and brittle. So that's how we, have adapted nature to how we, understanding the physics behind it, how we understand what has to happen in nature. So we'll also go on then to another kind of crystal with the sugar that we mentioned. So I'll try to do a sample here. Of course, when you want it to work and everybody's watching, it never does. But so this is pulled sugar with glucose, cooked to a high temperature, and then we've kept it under this lamp all this time. You can see how shiny it gets as we pull it. So it gets a very beautiful sheen because it's in that glassy phase. Okay, it's between a liquid and a solid in the glassy phase. And so we take off a pretty good hunk of it like that. It's hot, but it's not unbearably so. That's a little too small. I'm going to get a little bit bigger, make my life easier. Okay. Now, it's important here that the walls of this apple are all equal. So you don't, because we're going to force air into it, and we want it to expand at an equal rate. So it has to be not only equal in thickness, but equal in temperature. If one side's colder, obviously it's going to gel up, stiffen up, and hotter, it's going to be too soft. Okay. So we use the copper tube here, get it nice and hot. And we're going to enclose this around this copper tube so that it's airtight. So at this point, we're playing with that temperature between the glassy phase and the liquid phase it's already gone through. It's somewhat liquid now, between liquid and glassy. So we want to be sure that then as it cools, it's going to go into the crystal phase so it can wind up like that. Okay, so we put a little bit of, it's similar to blown glass, okay? It's not quite as hot as blown glass, but Still hot enough. So we like it. We want it to hang down like this so that the gravity holds it equally and starts to form like a very round shape. And at this point, it's still very malleable. I should show it over here too, I guess. So it's still very malleable, which means we can make the dimple on the bottom of the apple here, while we're still able to do so. And yet we still have to push this little part of the pump so that the air, it still stays round. Okay, now we have pretty much the shape that we want. The dimple's a little bit too big, so I'll bring it down. Now the top part is still very soft, so we want to push that down in a tiny bit. We'll let it stay nice and round there. Give it a little more air. Okay, we're getting it pretty close to what we want, so keeping it there, we'll put it in front of the fan. And now we're going from that glassy phase back to the crystal phase, where the molecules are realigned and they're rigid. They're not moving around like that, like Michael's slide. There is a little food color in here. There's no green sugar that I know of. And we can't add any natural ingredient like green tea or something like that, which as chefs we like to do, because you would disturb that crystalline structure and it wouldn't do what you want. Okay, it's starting to get firm now. Now again, we can't like dip this in ice because water is extremely hydrophilic. It blends with water easily. It would start to absorb and it would dissolve, just like rock sugar in your coffee. This would dissolve immediately. Okay, turn this back on. Okay, the advantage of the copper tubing here is that the copper gets very hot, and it will allow us to slip the tube out of the apple without getting the apple too hot. Okay, at that point, I'm going to reshape it a little bit. Get this plenty hot. This is the iffy part because it can shatter pretty easily. I was once doing a demonstration of a swan, so it's a little bit more complex, but same idea. You pull the neck out and the body, and so it was a really big one, like that. And the air pressure inside was pretty high, and it was in a small room, and somebody opened the door, so the air pressure that was around it changed and the whole thing exploded. That was the best demonstration I ever made. They really enjoyed that more than seeing the exploding swan. So all I have for you is a green apple. Thank you very much. I think we're good if you want to ask questions. Michael, you want to moderate?
Okay, so let's thank Bill. I guess you did. And there are a couple of people around with microphones, so if you have a question, we'll give you a microphone and you can ask. Question down here.
You said you served that as a dessert with ice cream inside. How did you get the ice cream inside?
Oh, thank you. I didn't mention that. We take like the hot scissors and we make a hole in the bottom, and then just with a pastry bag and a tip, we put the ice cream in the pastry bag and then force it in.
Doesn't the ice cream interact with the crystalline structure?
Well, eventually it probably would, but ice cream has a lot of fat in it, so it's not like putting a water-based. Oh yeah, did everybody hear the question? doesn't the ice cream interact with the sugar or the crystalline structure? If you leave it for a really long time, it would, but mousse that's held with gelatin or ice cream has a lot of fat, and it's emulsified and it's held together. So there's not a lot of excess water that can then interact with the sugar. If it was watery for some reason, yes, it would just dig a hole right through the sugar. But we do it sort of just before service too, so it's not, it can last a couple hours. Mm-hmm.
Another question? There. Microphones coming from both sides.
What was the most complex pastry or dessert you made for the White House?
The most complex dessert that I made for the White House. Well, the Chinese state dinner, we had to make 280 of these little apples. That's not complex, but it was time-consuming. We also made for them a chocolate pagoda. It was a really cool chocolate pagoda with a lot of petit fours and all that. But I think really complex in terms of what we're talking about today. We do an event every year for the Cooper Hewitt Museum, which is a design museum, and part of the Smithsonian. And so we did a lot of these kind of very sort of crazy and interesting molecular recipes. That was probably the most complex that I can remember.
So there are questions in the back. No, you probably do. You probably do. Okay.
Yes, yell.
So is it possible to make like a flavored green apple? Because you can't. Like, what if you use like that,
Good.
that lemon verbena concentrate?
It would probably crystallize. Yeah, it's very hard to flavor sugar that you've pulled. It has to be just pure sugar, and it goes to a really high temperature. So if you've added an oil or an extract, I'd be interested in trying this extract. That might work because since it would evaporate off, and some of the flavor might remain. So you've given me a good idea. I'll try that. I'll give you credit on the menu.
There's another question.
It seems as though the phase transition is just as important for the, if not more important, for the presentation of your food as it is for the taste. Can you comment a little bit about how you might focus more on one versus the other, and how one may sacrifice, or you may have to push the boundaries of one in order to sacrifice another?
Right. That's a really good question. Yeah, that's what I think every great chef is much more likely to err on the side of taste. So yeah, when you're constructing a dessert in your mind, you do want it to be beautiful. You want it to be appetizing. We say that people eat with their eyes before their mouths. So yeah, if we ever thought that it was really the flavor was going to be diminished by a decoration, I think it should be eliminated. We'd like to have a plate that is an organic whole, organic in the sense of everything fits together. So definitely taste trumps decoration. But there's many things that you can do which really taste great and look great. This does not really add, this apple does not add to the flavor of the dessert, but it doesn't detract from it. It presents it it's a vessel that is able to create a form that's interesting to eat. Since it's a sphere, that the ice cream stays cold and together like that, when you crack it, it sort of becomes available. So there's so many different parts of creating anything, a painting, a plate, whatever, or a formula. I think we all look for a very elegant solution, but yeah, sometimes you have to cut off the parts that don't look good. Easier to do in pastry than physics.
We need this side of the room. We've had no questions from this side of the room. It's terrible.
Hi. The sugar that you had there, at first I thought it was taffy.
Oh, yeah.
So I was just wondering, scientifically, how is that different from taffy?
Well, taffy has other ingredients in it, and taffy, of course, is a very old American tradition from the boardwalk of Atlantic City and elsewhere. But this is just sugar. It does look like taffy, but taffy remains somewhat in the liquid phase because it's still chewy like a caramel. due to it's called saltwater taffy, right? But you kind of stumped me. I don't know how to make taffy. But yeah, this has, it does have that kind of effect. We also, this can be used as pulled sugar, so I can get away from your question because I'm not really answering it. It's,
Well,
we
no,
also,
but Bill, the material properties are very much like that of taffy. It's true,
Yeah.
right?
Mhm.
It feels like taffy.
Just looks like
yeah,
the
it feels like
we
taffy,
made.
except it'll become very brittle, whereas taffy will always stay
Yeah,
soft.
but you know what?
Yeah, it's sticky too. Yeah. So one of the famous decorations is angel hair. You take this when it's much hotter, and you put it on a whisk and shake it back and forth, so you get this kind
it
of
is brittle.
effect, you know, but over and over again. So, and there's millions of things you can do. We do like a spiral, a slinky out of sugar. That's kind of fun, and a lot of different decorations that, as we say, it really just adds kind of an interesting visual factor, but it tastes okay. You can come up and taste it if you like.
So we need a question from this side of the room. Yes, very good. Well, it just seemed unbalanced.
Yes, you're
don't you
right.
think?
You're
It was
right.
unbalanced.
I like it.
What is President Obama's favorite dessert?
His favorite dessert. He really likes pie, and he is on the congressional record as loving pie. I mean, he's not a big dessert eater, as you might imagine. Nobody in the family is. They eat very healthily, but if they do indulge, either a pie or a cobbler, and especially when there's great fruits of the season, like farmer market fruits, peaches and nectarines, plums, apricots, all that stuff makes a great fruit pie. That's his favorite.
Another one from this side of the room. We're feeling unbalanced the other way.
making
Yeah,
up
we're making
now.
progress.
Yes,
yeah.
Hello? Yeah. How do you figure out what the temperatures are for like a certain point at which, you know, you turn it either crystal or glass or the liquid?
For
do
the
you do
sugars?
research before, or do you do like trial and error?
No, it's already been done, you know, for me. They're basic recipes that we follow. No, I'm serious. There's, these are recipes that people in my business, you know, already know and pass down. What's interesting now, though, is that when I first started, and it was a long time ago, the chefs, you know, you would ask the chefs, well, that question, you know, what's going on here? Why is it doing this? Well, never mind about that. Just do it the way I told you to. So, but what's incredible is since you have people like Hervé Thies and the Harvard Food and Science program, chefs can now understand what's going on. And you don't have to be, you know, just go back in the kitchen and shut up. You can really understand why that thing can be created. So that's a really cool part of my profession now.
So in the back, we're going to make the microphone run. Exercise for the people with the microphones.
Yes, let's move.
So 2 questions, one
Yes.
real and one less real. The first is you mentioned that you had to have at least 60% or so cocoa for making your mousse with the water. So I was wondering what other foods you could use with the water to make a mousse, be they like a coconut or an avocado, what basis of the fat content? And the other question is, you said President Obama likes pie, but how does he feel about tau?
About what? Oh. Physics joke. Yeah, we have to clap because it's a formula, right? So you said like that? Is that what you're talking about? Okay, nice.
Tau
Now I
is
forgot
to
the first-
pie.
Oh, okay. I forgot the first question about, oh yeah. I'm easily distracted. 60%, yeah, that I should have explained it better. You have that picture of the cocoa pod up there. So we talked about cocoa mass and cocoa butter. But cocoa butter, when it's cold, becomes very stiff. That's why it can form this kind of thick mixture or this ganache. But if you were to use another ingredient, it does not become stiff at room temperature. So avocado or one of the other ones, you would have to add gelatin in order to have, more gelatin I should say, in order to have that effect. 60% cacao merely means that when somebody tells you, and this is kind of I don't know, bogus thing about quality chocolate. People always say, oh, I like 60%. Oh, I'm better than you. I like 70%. Well, I'm better than you. I like 80% chocolate. All that means 60% chocolate means that you have 40% sugar. So you could say, oh, well, 80%, that must be better than the other one, but because it's only 20% sugar. But what's important is the quality of that bean, not the percentage. So that bean can be very rich and very fruity and great flavors, and it depends on how it's roasted, how it's fermented. All that goes into making a great chocolate. So you can have an excellent chocolate that's 60%, 60-40, and a very poor one that's burnt and overly roasted and not very flavorful. So the percentages kind of are an indication of what's going on, but not entirely.
So I think we're going to take one more question. Bill is going to sign books afterwards outside, and I want to make sure that people are around for that. The gentleman in the back, you're raising your hand, right?
Is window glass a liquid or a solid?
Oh, yeah, right. Thank you. Thanks for...
What do you think? So,
Oops,
I would
careful.
say, so it's a liquid, so I would say it's a liquid, but it's a liquid which flows very, very slowly. So, I mean, it's the same with this stuff. It's like the taffy question. Is this a liquid? Oh, now it's
Now it's a solid.
Now it's a solid. We messed it up.
Yep.
No, but it's still, now,
Still somewhat.
yeah, see, say again? And it's always a liquid. Yeah, so everything is actually, okay, so I'm going to mess this up. I'm going to be completely confusing. So, so the thing is that when you say something is a liquid or a solid, so Dave will either get mad at me or not here. This is sort of a test. When you say that something is either a liquid or a solid, I mean, it's really a matter of definition. I mean, if you jump into water from an enormous height, it behaves like a solid. So it's a matter of the time scale. So one of our equations of the week in this class is actually the time scale that any material has associated with it. So every material has a time scale, which is the time scale essentially for the molecules in the substance to flow over each other. And in water, that time scale happens to be very, very fast. It's nanoseconds or smaller. And so basically because of this, if you hit the thing at the time scale of nanoseconds, then it behaves like a solid. The molecules don't have time to move. In the same way, with this stuff, you can see what the time scale of the molecules moving is. It's the time scale that it takes to stretch it. So everything is really a liquid or a solid. It's just a matter of time scales. How's that? Okay, so wait, but that was the last question. Oh, that was great. Okay, that was fabulous. Okay, so let's thank Bill. Okay, so next week we have elasticity, so that's solids. And right now Bill is going to go and sign books. Maybe he's going to work his way up. I think that's what I was told you were going to do anyway. Yeah. Is that what you're going to do? Say again? Oh, alginate, you didn't spherify. Oh.
Thank you. I forgot. How did we lose that? Okay, remember, this is a salt, has a salt, it's gluconate. This is alginate. They don't react on their own. They only react, thank you, when they come into contact. So,
We need the camera. No, Bill, maybe
oh, good. I'll come over there.
Maybe you should come over here.
Yeah, absolutely.
In fact, it's not going to be the same.
Oh, we have to give you, thank you for, how did I miss that?
Hopefully it'll work. The problem is having a good camera. If it doesn't work, you're really in trouble.
Okay, and we like to add a little, like you can add little violets or fennel flowers or lavender or jasmine flowers in there. Is that? Oh yeah, I'll just put it in here, I think. Yeah. So, yeah, I did. Okay, so gluconate in a liquid, which is a honey made from our honey there. And so you can dump it into there. Let me take a little, yeah, thank you. So it's oftentimes it's easier to see because you have like a fruit puree or something, strawberry or mango. So here it's clear on clear, but I think that's kind of cool. So as you can see, as soon as it touches the alginate, it's starting to form that matrix. Leave it for a minute or two. I'll make a really big one, it'll be easier to see. Well, oh, okay. Yes, it's honey and water with a few herbs added, but the gelling agent is a salt called sodium gluconate. And then this is alginate, which is a gel made from algae. So you're, neither one of them acts fully on its own to make the membrane. It's only when it comes in contact one with the other that the membrane is formed. I'll put more lemon in this one so maybe it's easier to see in this light.
This is where the green food coloring would become useful.
Yes. Oh yeah, this is good. This is like this is going to be a lot cooler. Did that answer your question about the salt? So it's just a kind of sodium, so that's why we refer to it as a salt. These products, by the way, if you're planning a dinner party, are available through a company called Texturas, which is Ferran Adria's company, and they come with recipes and very easy to use. So this is the type of thing which we might put on top of a little cookie or a little mousse or something like that, just to add this kind of mysterious element to it. This should be easier to see. Okay, so this kind of little blob.
So I think that we should clap. That